20.5 and 20.7 contain the reactions for the remainder of the chapter. So I'm going to see if I can't put these two together here into one little lecture segment. So the first reaction here is in terms of the general reaction. The reaction of a Grignard reagent. Obviously that can be bromide or chloride or iodide. And I'm going to add or a lithium reagent, because either one of these will work. If you react that with carbon dioxide, what's the structure of carbon dioxide? So of course I can't cover the screen from this side, but that's a carbonyl. So this is a very good electrophile, and the Grignard attacks that electrophilic carbonyl, just as we've seen with many other functional groups. And upon working it up by adding acid, you obtain the carboxylic acids in excellent yields. So that's the general reaction in these work for alkylithiums or Grignard reagents. So a standard example of this might be a substituted Grignard that would have been made from the bromide. You'd know how to make that methoxybromo compound now. You can then react that with CO2 and obtain good yields of the corresponding, and I'm going to move those substituents just to make it easier to write here. There's the desired carboxylic acid. So that's actually section 20.5. Now, in 20.7, the first new reaction there is dehydration of amides. We're making nitriles. So that section is on nitriles. There are several reactions here. And again, the general reaction is if we have an amide, but it needs to be what we would call a primary amide. So these hydrogens are required. You've got to have two hydrogens on the nitrogen of the amide for this reaction to work. You treat this with a dehydrating agent, and you heat it up a little bit, and you remove the water. And of course, if we remove H2O, what we're left with is the nitrile. So, just a simple example, the benzoic amide, that's benzamide. If we treat that with thionyl chloride, that just bring down those conditions from above, we would make the nitrile. Okay, so that's the first reaction in section 20.7. That's how we convert an amide into a nitrile. We do dehydration. So of course, what's the reverse? The hydration, or we would say the hydrolysis, of a nitrile. Okay, so again, in terms of the general reaction, we take a nitrile, and we're actually going to combine two reactions into one because they're so closely related that I want you to see the connection to them. If we take this, of course, we're going to have water, right? We took H2O away, so we're going to have to put H2O back. And this can be done under acidic conditions or basic conditions. Okay? Obviously the mechanism will be different in those two, but we can begin to decode that now. So the first intermediate that we could actually isolate here is in fact the amide. So that's just the reverse of the reaction we looked at just a moment ago. But we're not done. This is an isoluble intermediate in many cases, and often you'll heat these a little bit, and if you heat them gently, you can stop with good yields of the amides. But if you continue to heat them for longer periods of time, H+ or OH again, they will continue on and produce the carboxylic acid. All right, so that's the hydrolysis of the nitrile. In many cases we can stop at the amide, or we can continue on to the carboxylic acid. So again, looking at a simple example here, but a specific one. Let's do the benzonitrile, the benzylic nitrile is what I mean by that. If we hydrolyze this, first gently with acid, we would produce this amide. And if we continue then, heat it further, we can go on to the corresponding, oops. All right, we can go on to the corresponding acid. Okay, so that's hydrolysis of a nitrile. Now, there's another very useful reaction of the nitriles. Now, the nitrile, you recall, the carboxylic acid and the carboxylic acid derivatives, we have a polar bond here that's polarized in this way, so there will be a partial positive charge on that carbon. So not surprisingly, these react well. Here again, this is going to be our general reaction. You can react these with a Grignard reagent. I guess my default is the bromide, but any Grignard would work without regard to the halogen. And that acts as a nucleophile and will attack that carbon. Okay? So first, to finish the general reaction, what you actually get here, let me put R' on that one, is you get the ketone. So that would be a useful way to synthesize ketones. Are you making yourself some flashcards or some lists perhaps in terms of how do I synthesize particular functional groups? We've got alcohols now. We've got aromatic rings, obviously. We have carboxylic acids, and we're about to get into all those derivatives. We've got aldehydes and ketones and alkyl halides. Do you have a list of those? Because you see, when you face a problem on the exam, if you have a list in your mind that you've already made of ways to make functional group X, whatever that functional group is, then the amount of information that you have to process and digest is much smaller than the whole of our course. So make those lists of specific things that you're trying to synthesize, as well as lists of reactions that make specific kinds of bonds, like carbon-carbon bonds, carbon-oxygen bonds, carbon-nitrogen bonds, and so forth. All right, so how do we get at converting a nitrogen to an oxygen? Well, I put up this partial mechanism intentionally here so that you would see the initial addition is going to produce this amino-anion. Okay? That's an amine group, and it's been deprotonated, so it's an anion. And that is a stable species in solution, and then on workup, which is going to be some sort of aqueous workup, it hydrolyzes the imine to the ketone. This, of course, would be almost certainly done with the mildly acidic workup. All right, so that's using the nitrile as an electrophile. And then there's one more. The reduction of nitriles. Now, let's look at this with our general reaction. We have the nitrile, and we have our very powerful reducing agent, lithium aluminum hydride. Okay? That's a powerful reducing agent, and it reduces this all the way down. I'm going to put the hydrogens on here explicitly in both places so you see them. The ones attached to carbon come from the lithium aluminum hydride. The ones attached to nitrogen, as we're seeing in many of these reactions, the nitrogen, the heteroatoms end up with their hydrogens as a proton from an aqueous acidic workup, typically. So we can do this reaction under lots of different kinds of conditions. You might have a chiral center, and you need to be careful with this because lithium aluminum hydride can be basic. But if you're good and you understand your reaction conditions with LaH, of course this would not, at least so far what we've learned, would not impact that chiral center. But again, we're going to learn soon about the acidity of these alpha positions. Oops, that was supposed to be the nitrile there. I'll draw it in with that we might have gotten from an SN2 displacement of a bromide at that benzylic position, for instance. Okay, so the textbook has good mechanisms for these. I don't feel the need to write those mechanisms out for this particular section. They're pretty straightforward and involve common intermediates that we've seen many times already. All right, so that's chapter 20.